Hi everyone, I'm Daniel Marcous from Waze, a social navigation app owned by Google, and I'm going to talk to you today about something that I call full cycle data science. It's a way of work for data scientists, and as you'll discover it and adapt it, for us it sort of became a way of life. And we'll see how to do it and implement it using the Google Cloud Platform tools and show the specifics of what we did at Waze for that. At Google, machine learning is really the core of everything we do. Google products and Waze, for that matter, are really based on data and are intelligent products. And in order to power intelligent products, you use machine learning and data scientists to build these machine learning models. Now, this isn't really something new, but in the past, it was really called an algorithm developer. So someone that would come up with this piece of logic that's core to the app and would make it intelligent with coding some rules and patterns of how things work. But as the world matured and progresses, we've realized that in order to make our algorithms as efficient and provide as much value to the user as possible, you can actually give a machine the ability to create them on its own. And that's basically machine learning models, which are built by data scientists. So this role, as it was in the past, is now the data science role. And you can see that in a lot of Google apps, where the core is very intelligent and powered by machine learning. So in Waze specifically, the very core features that you have in the Waze app are predicting the ETA, meaning estimated time of arrival, or how long is it going to take to drive from A to B, and choosing a specific route for that user. For the Waze carpool app is matching riders and drivers together to take joint rides. And for the ads product is serving the right ads at the right time. All of these are powered by machine learning and are built by data scientists. Now, in order to create a successful data science unit in your organization, you have to do several different things. And this is how we look at it at Google. Now, it doesn't really matter if it's a single data scientist or a really big organization with a lot of different data scientists, but you still have to make sure that these are part of your goals and what you're aiming to. So first and foremost, it's super important to have impact and to really affect the product and provide value for your users. Now, I'm saying that explicitly because this is a bit different than another role which is sometimes confused with data scientists, and this role is called research scientist, where the goal of that role is to advance science and produce papers and state-of-the-art methods. Now, for data science, we're really production and product-oriented and aim to make a visible impact and improve value for our users. Now, in order to actually do that, with the load of tasks that you have for a data scientist that, as we said before, kind of replaced the old style algorithm developer and now is in charge of every piece of core logic in your product, you have to keep up a really high velocity factor, meaning you have to keep your projects going, you have to deliver results in a timely manner and not take forever for every project. Now, with all of that, you still have to maintain a high standard of quality. And if I'm talking to data scientists here, you all probably know that data science isn't a really easy task. And building high quality model is hard, and very often really small things that you might miss, like something wrong with the data, some value missing or things like that, might have very catastrophic impact on model quality and what you see later in production. So all of these are very important. Now, in order to actually create a product that's powered by machine learning, and a machine learning that's production grade, what we call, that we're trusting it to serve hundreds of millions of users, you have to do a lot of different things that are sort of out of the data scientist's comfort zone. And if you put it on a scale, as you can see here, then on one hand, you have all the tasks that are related to the logic of the algorithm that you build. And that's the classic data science-like task. It has to do with data cleaning, exploration, feature engineering, modeling, which is the fun part, actually training models, and evaluation, trying to make them better. But that's not it. In order to get a really production-grade product, you have a lot of operations in the other side that you also have to take care of. And that has to do with data validation, so making sure that the data that's streaming through the system and going in is actually the data that you've trained on and looks the same way. You have to take care of scale, especially if you're handling big data and apps with a lot of users, either scale of training on very big data sets or scale of inference, where you have to set up this server to serve model prediction calls from a lot of users in parallel and do it in very low latency. You have to deploy models to production servers, and you really often have to do something that people don't really talk about, but it's something like deploying data. So if you do some feature engineering and you want to have these features available later in production in real time, then you actually have to deploy these feature computations to some streaming environment to have them available for your backend servers. And on top of all of that, you need to add monitoring, alerting, orchestration to make sure everything ticks, nothing fails. And all of that is fairly complex. Now, in a traditional organization that has a data science unit, you often need two functions to operate this full scope of what's needed for a production-grade model. You have this frustrated data scientist there in the middle, which really wants and likes to do model training and feature engineering, but keeps being dragged to more operations, validation, writing their code in a scalable manner. And you also have to have someone that's really operation-oriented, which you often call the DevOps person, data engineer, ML engineer, SRE. Every company says something different, but that's someone that's in charge of operations, of deployments to servers, and works in conjunction with the data scientist of making sure that this app is production ready. Now, in old school organization, you actually even have to add a third function on top of that. Because when a data scientist does research on her isolated environment, let's say that's an R server where you write some R code, and the entire backend of your organization is written in Java, something that's able to run in production, you actually have to rewrite everything from R to Java. And usually give that to a backend engineer, which takes the R code and uses whatever they have available in Java, which is obviously not the same. You have some slight implementation changes. You can try and do it fast because that person that re-implements it is usually not a data scientist. And it really results in very strange issues that are not only hard to fix, but very hard to detect. And I've experienced all of them on my own flesh. So trust me when I say that. Now, I'm going to show you a different way. And I'm claiming that in Waze, we have a different method where a single data scientist can focus almost solely on logic and get nearly all of the operations out of the box. And that's what we call full cycle data science. And in this presentation, we're going to show how, why, and give you the tools to do it yourself. Now, just one more note here is that a very important part of doing it is generating independence for the data scientist to contribute to production. And that has a lot to do with breaking the dependency between data scientists and DevOps and backend engineers, and really having data scientists close this full product cycle and being independent in their releases to production. Okay, now, as I've said in the beginning, this is a Waze flavored solution. So it has been battle tested in Waze, but I really want to say here that we didn't start that way. All of the mistakes or other approaches that I've showed in the previous slide, I've actually made them. And as time went on, and as we realized that things didn't work smoothly, we thought, okay, we can do something better. And we've slowly improved and improved the way we work. And now it's sort of our life methodology of how you do data science. And we're really happy with it. It's working really well. And I'm going to share some success stories and how we do it. And we thought it's going to be a good time now to start sharing it with the world. So hoping it's going to be helpful. Now, let's deep dive a little bit more into the challenges of why we actually need it and why it's even that hard for a single data scientist to do all of that thing. So it happens to be that there's a really good paper that I recommend reading called Hidden Technical Debt in Machine Learning Systems. Happened to be that it was published by Google. But basically, it talks about why it's that hard to get a production-grade system that's powered by machine learning. Okay, now I'm going to summarize this entire paper in 2 slides. So bear with me. This paper is a lot more detailed, and you're very welcome reading it. But it boils down to something like this. When you do research, you write your machine learning code in your isolated environment, and you really do things like hyperparameter tuning, choosing the right model, sometimes some feature selection, and coming up with an evaluation method. But when you want to take this successful model from your notebook and deploy it to production into a real product that's serving users, you actually have all these other boxes that are around the machine learning code that not only you cannot neglect as they are crucial for the success of your product, they're almost impossible to do inside an isolated environment that's not connected to the rest of your product. Moreover, if you look at some of this, like serving infrastructure, it's not something that's in the comfort zone or the skill set of a data scientist to own and to be able to manage successfully, especially when you're talking about really large scale. Now, to add a little bit on top of that, and data scientists know that for a fact, the modeling fun part of training models is actually not the biggest part of your work, where the biggest part of your work is data cleaning. And I'm specifically putting this here because I want to emphasize that data cleaning in isolation, in your notebook, on a static data set, is so much different than what you're going to expect and see in production, where you see streaming data and you see new versions of your application and of backend servers changing the way they write their logs. Data is constantly changing, and when you deploy something, you will more often than not see data that you've never seen before on your static environment. So this super important part of data cleaning actually looks very different between research and production. And if you work with data scientists on a regular basis, you actually know that 80% is cleaning and 20% is complaining that the data isn't clean enough and coming back to the backend developer to ask for cleaning in the logs and logging some more data and things like that. Okay. Now, all of these different boxes that we've showed before are not sequential. They're not in this sequential order, and you also can't do them in parallel. they're actually a part of a cyclic process, okay? And this is a really nice graph by the Uber machine learning group, which I really like, that shows its data science life cycle, which often starts with definition of what you want to do, what you want to measure, what you're aiming to optimize, and then it goes to the prototyping phase. And the prototyping phase is often this really small red box that we've showed before with the machine learning code. And as you can see here, you can actually make this little red box of prototyping fairly complex and do some data manipulation and exploration and feature selection and evaluate different types of models. But after you're done with that, you have to go to production. And that has to do with deployment of models, of data, and you have to do web measurements. So you have to set up your feedback loop, you have to set up your monitoring, you have to set up experimentation. You often don't want to just introduce a new model to 100% of your users just like that out of the box without testing it first. And when you do some of these processes and different steps, you're very often discovering that, oh, wait, this model isn't really working. I probably missed something, whether I've defined something wrong and I have to go back to step one, or whether I missed some part of the data that isn't clean enough and has some anomalies that I need to go back and clean in this data processing code. So that's why it's really cyclical. And it is a common case to actually find these things only in production, only when you deploy your model and use production data. Now, not with actual user, but often the safer approach would be a side-by-side test or an A/B test. So you'll see production data and production workloads, but not affect users with bad predictions. Okay, now, a very small but important note that I want to show here is this distinction in the terminology. Now, we're talking about full cycle data science, okay? Full cycle meaning closing this full product cycle from idea to production with a single data scientist without any other dependencies. We are not talking about full stack, which is another completely different terminology that usually refers to someone that owns expertise in the entire technological stack and involves backend, front-end, automation, DevOps, and all of that. It's actually the contrary. I'm going to claim that a successful full-cycle data scientist with the right tools should only master a single skill set, which in the Waze case is Python coding, and that's it. So we're back with the question. We've seen this really complex process, really complex life cycle with all these different skill sets, and we're wondering whether a data scientist can actually handle all of it. And a data scientist is often someone with a statistics background or a mathematics background, and more often than not a software engineer. So you do have this exceptions of people that are actually interested in everything and want to do both science and engineering and are interested in DevOps, and they're a really great asset, right? They can maybe get something to production on their own, taking this job of the 3 different people, probably less fast because they'll do all the work, but it's not what your organization needs. It's not how you generate scale. It's not how you generate velocity. You want a data scientist to do what they do best and get everything else as well. Now, I'm claiming in this talk that, yes, a data scientist can do all of this, but only with the right tools. And that's a really important distinction, only with the right tools. It happens to be that Google Cloud Platform has the right tools, which we're going to show exactly what are they and how to use them. And just a small note here is that if you're not familiar with it, Waze was actually running on AWS infrastructures and was ongoing a very large migration of everything to Google Cloud Platform. And I can really say confidently, using both infrastructures, that in the world of what Google Cloud Platform calls AI, basically tools for data science, really GCP is very advanced and by far more advanced than the competitors that I've seen, at least. So you're in really good hands choosing these tools. But I'm not claiming that other options do not exist elsewhere. Okay, so let's talk about the data science evolution and how you're going to get to a 2020 level full cycle data science. Now, some prerequisites. We said the right tools. So what are these right tools? What are the characteristics of these tools to enable what we call full cycle? So first and foremost, what I think is most important is simple. Now, when I say simple, I'm not saying that what the tool does is simple. I'm saying that it's simple to use. It's easy to use. It has a convenient SDK. It's easy to understand. And it's really important because there's a bunch of different tools and a really long life cycle that you have to integrate everything into. So simple tools are a must. Now, to counteract that, you actually want the simple tools to also be customizable. So for the, let's say, 10% rule of thumb use cases that you have for your company that are super unique and are not offered by the tool as a default, you will have the ability to customize and do your special machine learning magic that's specific to your company. Now, on top of that, you want them to be as much managed as possible. And when we say managed in cloud tools, we mean you don't have to take care of servers. They get taken care of for you. And that's a really huge plus, because when you start handling with the size of memory, disk, CPUs, different regions that you have to deploy your servers to, different dependencies of the operation system that they have, deploying code to them, it starts being a mess, and it starts being a pure SRE DevOps work, and that's not what you want your data scientists to do. Now, on top of all of that, you want them to be scalable, because you want someone, your data scientist, to write their code in their notebook the way they're used to with Python, and have that seamlessly run in a scalable manner on huge data sets of terabytes and petabytes of data. And you also want that to code to work for inference in very low latency. Now, I'm adding this other thing here, which you can see slightly in italics, which we say Pythonic. So that's the Waze flavor, Pythonic. Not saying Python is the right way for everyone, but strongly recommending that you just choose one. So you have a unified stack, and your data scientist would need to have the expertise of a single coding language for all of the stack, the technological stack that they need to operate. In our case, it's Python. For other places, it might be R. And that's really important. Now, it happens to be that Python is really the most common language for data scientists, and it's really popular in operation tools and SDKs. So I really recommend Python, but if that's not your thing, totally feel free to go with something else. Just remember to keep it unified across the stack. So let's talk about tools in specific. So I've put this distinction into 3 different categories of tools for the full cycle data science stack with GCP. So first, we're going to talk about data tools. Okay. So when we talk about data, you have to store the data somehow. You have to have your inputs for your training and inference jobs stored somewhere and your outputs, and you have to do all kinds of data processing on top of them. So Google Cloud offers BigQuery, which is a managed processing engine, happens to include storage as well, which we're really heavily using. It has a SQL interface as a first class and a Python SDK as well, and really super convenient, super easy to use, and seamlessly scalable. You have Dataflow. Dataflow is the Google managed flavor of batch and stream processing. And I'm mentioning it specifically that it's TFX integrated. And you see the T there in parentheses because if you're talking about the subcomponents of TFX, we're using actually TF transform, which is whole kind of magic that we're gonna talk a little bit more about later. That actually gives you the ability to write Pythonic TensorFlow code, which behind the scenes translates into Beam code running on Dataflow. And that way you can actually use the same code that you're writing for feature engineering on very, very large scale batch and on streaming data in real time. Use the same code, which is only TensorFlow code, and you don't have to learn all of this moderately complex Dataflow SDK. But behind the scenes, it's powered by Dataflow. Now, on top of that, you actually have to have some place to store your features, which will be accessible in very low latency. So there's a key value database that we use in Google Cloud. It's called Bigtable. The equivalent open source for that is Cassandra. If you're familiar with that, really common to use. Now, in terms of the scientific stack, so there's a whole suite of tools in Google Cloud called Cloud AI Platform, and we're going to call it CYP to kind of talk fast here. So this suite includes a bunch of tools. I'm just going to name a few. And we're going to start with CYP Notebooks, which is basically a managed but highly customizable platform for research and exploration based on Jupyter notebooks. Okay, so that's where you do all of your exploration, start playing around with code, playing around with data. It actually is integrated with all of the rest of the stack, so you can actually deploy models from there and run training jobs from there, which leads me to the second component, which is CYP Jobs, which is the scalable training infrastructure. So this tool actually allows me to send my logic, which my logic is, okay, this is my model code, and this is my data set. CYP Jobs, please take both of these and run the training for me, and you will decide how much resources I need. You'll set up the machines, you'll scale them, and just come back with the model when you're done. Really cool, really easy to use. I have TensorFlow in parentheses there because although it does support scikit-learn models and XGBoost models, there is a bunch of features that are unique to TensorFlow for scalability and works very well with TensorFlow there. Now, in my mind, the cherry on the top here, and this is the one product that you should actually remember from this talk, and you should definitely use. Even if you're not running on GCP and you're running on AWS and you want to just pick one, it's still worth using, and that's CYP models. So that's basically serving infrastructures for models that supports auto-scaling and low latency inference, which in common words means once you have a model, okay, so if it's TensorFlow, it's the saved model object. If it's XGBoost or if it's scikit-learn, it's the pickle object that defines the model. Once you have that, you just give it to CYP models, and it will spin up a microservice with auto-scaling, with out-of-the-box monitoring on latency and on errors, with integration to feedback loops to do auto-evaluation, and with a REST API, so you can integrate with it with every kind of technological stack that you want, all out of the box. So you can see where I'm going here with my head of you only need to know Python and you only need to know the data science skill set and you get all of the ops out of the box. So this is the one that's pretty much covers 50% of the ops that you have in production machine learning systems. Now, there's a bunch of tools here. You need somehow to glue all of them together and to have a single pipeline training the data, then pushing the model, deploying it to site models, then doing the evaluation and all of these things. And that's exactly Cyclic Pipelines, and it's powered by TFX, TensorFlow Extended, which we're going to talk about in a few slides. All of these, by the way, support Python SDKs. Okay, TensorFlow. So at Waze, we've kind of made it our goal here because of all of these different toolings and all the pros that I have here on this slide to use TensorFlow 2.x and onwards for modeling and not do Scikit or XGBoost, because TensorFlow 2.x is really production grade and battle tested in very large scale. It's really easy to distribute it and get very good performance for big data training and for low latency inference. It has very good integrations with all the Cyp stack that we've seen. It supports the data science classical fit predict paradigm for training and predicting and evaluating models, which is really fun to use. And it has a really rich ecosystem of these other components to analyze performance, to do transfer learning, and all of this kind of amazing stuff. Now, things that people don't often know is that the high-level API for TensorFlow, which is called TensorFlow Estimators, actually has out-of-the-box models that you can really use without tuning or with slight to no tuning. And they don't only support neural networks. You also have logistic regression there and gradient boosting. So if you decide that you really love gradient boosting and you really want to use that, you can actually do that in TensorFlow really out of the box. Now you have here in this small box, black box on the side, link to a fairly long course that I sometimes give at for communities and internally at Google about grasping the basics and how to use TensorFlow 2.x. So feel free to use and see more details there. Now TensorFlow Extended that we've mentioned before is an open source framework for managing machine learning pipelines from end to end. But with AI platform pipelines, you actually get it managed because it has a lot of different components, TensorFlow Extended, and it's not really easy to set up, maintain the database that it has for metadata and all kind of other things. So basically, AI platform pipelines is the managed version of TensorFlow Extended. Now, what TensorFlow Extended, or for short, TFX, gives you is out-of-the-box components for serving and for training and serving time transformations like feature engineering. And that's what we've mentioned before about TF transform. It's part of the TFX stack. It also gives you out-of-the-box tools like SKU detection for your data between training and serving. It gives you components like Model Pusher, which is a component that is looking for your latest, most updated model, compares it to your production model, and only if it's better on an holdout data set on evaluation, only then it will deploy it to production. Very cool. All of that and more are some of the components that's there, and it's highly customizable, so you can add all of your magic machine learning components and smart ideas, like with a very few less than 10 lines of code. So how all of these come together into one unified technological stack? Now, it's a lot to grasp, so I'm just gonna go over it slightly from the left to the right. I'm gonna use my pointer here. So we're starting with data, obviously. So we have batch datasets that are available in the BigQuery engine that we've mentioned before. And we have streaming data that's available in the GCP messaging system, which is Cloud PubSub, it's called. And we usually have both, right? From events, from logs, and things that people do in the app right now. We needed streaming, so we have that available in Cloud PubSub, and from data sets around metadata of who is this user, like a user database. So that's in BigQuery. We have this processing phase to do the feature engineering using TF transform. So it's TensorFlow code that behind the scene is translated to Dataflow code. And we have this outputs of generated features and sort of inference dataset and training dataset stored in BigQuery for large-scale training. And in Bigtable, the key value store, as a feature store, somewhere to have accessible real-time features for inference. Okay. On the other side here, we have the Cyp stack, where you kind of mess around with the data and the models on your Cyp notebooks, and then you deploy, sorry, not deploy, but train large-scale models on this data using Cyp jobs. On our case, powered by TensorFlow. Also, one small thing that I forgot to mention here is that you have real-time feature data in Bigtable, and you have sort of static, let's say, daily, periodically updated data in BigQuery, but you can actually query them both from the BigQuery API with pure SQL if you're using a cool feature called federated tables. So this Bigtable table with your features would actually look like a SQL table that you can join with. Okay, now on top of that, in production, you have the Cyp models, which is the model server, the model server holding your production models, getting requests from predictions from the microservices that you can see here in the bottom. And for the more advanced use cases where you can actually add custom code in Cyp models. So it's not only .predict on the model that you send there, it's .predict and run your own code. You can actually look up features. So you break dependencies even more. You don't need the microservices to send you the features for you to be able to use them for prediction. You're just getting a prediction request for, let's say, user X, and you go and you fetch user X's feature values, and then you compute the prediction, and then you return the prediction to the microservice. So you completely break the cycle, and now you don't even need backend engineering, DevOps, anything to change the features that you use. You can add new features, you can remove features, you can change feature engineering code, all by yourself as an independent data scientist. Now, if you think that's cool, wait for the next slide to show some more advanced capabilities on top of that to handle the continuous integration and continuous deployment of machine learning models into production. So you start with machine learning code, and that code is actually the logic. You focus only on that. You write feature engineering, and you write your model. Let's say it's a feed-forward network with 3 layers, okay? When you push this new code to your code repositories, you can actually configure something in Cloud Build, which is the CI tool for Google, to go and fetch that code, send it to Cyp jobs, rerun the training with this new code, save this new model in your model store, then call the model pusher that we've seen before from TFX, and have that model pusher compare this new model to your production model. And if it's better, automatically deploy to an experiment or deploy it to production by just one command of changing the labels in Cyp models. So inside models, you can actually keep versions models under the same name. So you can say like, this is V1, this is V2, this is V3, and you can give them labels. So like the Waze flavor of how we use that is that we use labels of prod label, staging label, canary labels like A and B for experiments. And you can have that automatically update the labels for your new model to say, okay, this is now production. And from now on, all new traffic to the model goes to the new production version of the model. Again, you don't have to have backend server deployment cycle in order to deploy new data science models, completely breaking the dependencies there. Okay, so coming back out to a high-level view again, full cycle data scientists, what they actually do is, what you see in bold here is more focusing on the logic side of it. It's the research, the exploration, the data processing, which we often call feature engineering, and the modeling and evaluation. Now, all of the rest of the tasks that are not bolded here are still tasks that a full cycle data scientist does, but you're getting most of them out of the box for you. So that includes experimentation, measurement, productionization, whether it's orchestration or automation, scalable inference service, monitoring, alerting, and so on. Okay, so what did we gain here from doing all this full cycle data science work? And this comes back to our life goals in one of the first slides that we had there. We're gaining a lot in terms of velocity because we're reducing handoffs between different functions. We're getting more quality because data scientists owns cleaning their data and they're not handing it off to anyone else, and it's only a single function. And as we said before, this is the most important part of your job as a data scientist and the most time consuming, cleaning data. This is also, as research shows, and undoubtedly shows, that cleaning the data and the quality of the data that you give to your models is the #1 factor in model quality, and not the hyperparameter tuning, which is a second step. So having the data scientists clean their own data that they use for their model is, in my opinion, crucial thing. We also gain ownership, as the data scientist in this case cares about production system because they own the production service that serves prediction. They own the monitoring, they own the alerting. They actually have a production service serving hundreds of millions of users in Waze or Google cases, which are super important and connects them to the product. Now, all of that together really encourages a sense of satisfaction, which is an added bonus, which is super important. Now, when a data scientist doesn't only do research, but does production and sees their impact on users, generating value, having this sense when you click something and you deploy to production that traditionally only engineers had, you gain this sense of satisfaction, and data scientists are a lot happier. I can say that on myself as a person, on my team, and for data scientists as a whole in Waze. Okay, coming back to this slide that we had before there, idea to production and focusing on the logic. So we've just showed how you can do all of this with one data scientist owning the end-to-end product lifecycle, focusing almost solely on logic. I'm saying almost because you have to have some sort of understanding of what's happening around you. And you have to do a bit of configuration for that. But you get nearly all of the operations out of the box. Now, more than that, really important to state here again, is that the production grade model and production grade code is extremely similar, if not exactly similar, to the draft model code that you wrote in your notebook. Because now when you're using things like TensorFlow transform for feature engineering, you can actually deploy the same code to work on large scale training data and on streaming data in real time with the exact same code. No re-implementation needed in another language, no tweaking to have this in batch and that in streaming. It's the same thing. It works the same way. And it's TensorFlow syntax. Now, we've handed tons of credit to data scientists here on how they can do things with the right tools, on how they can focus only on logic. But there's a bunch of tools, right? And we've shown how this whole data science technological stack comes together. With that said, it's worth mentioning that it's not easy to make all of this stack come together and have the requirements that's specific for your company. And that's where data engineers come in. Okay, so maybe different companies will call that differently. We call it data engineers. It's practically software engineers building tools and systems for data practitioners like data scientists and product analytics in order to facilitate the practitioner's job focusing solely on the logic. So we have these tools. They don't actually need to build tools a lot of the times, but they have to configure them. They have to integrate them. They have to write a lot of what we call glue code to have this flow together between all the different tools. They have to write a lot of automation and orchestration and set up the platforms, set up the code templates that a data scientist could just fork an existing project and change the logic section, change the name of the data set, and you get everything out of the box. Now, it's not an easy job. It's an engineer's job. You do need an engineer for that. And it's super important. But that way, you don't have an engineer supporting a specific product feature. You have the data engineer support your platform as a whole with better tooling. And that alludes me to a very small caption that I'll say here. There's a really nice article by Stitch Fix, really articulating why engineers, or data engineers in this case, shouldn't write ETLs and data pipelines, but should build tools. And that has a lot to do with what we said before about data scientists needs to do their own data cleaning, as it's super important to understand your data that you use for modeling. Now, does full cycle data science end with tools? Well, not exactly. It's not only tooling. Tooling is equally important as culture, which you can often see online, people talking about engineering culture and not often talking about data science culture, but it's really important to work in the right manner, not only with the right tools. And the flavor that we've adopted for data science culture at Waze is being impact-oriented, as we said at the beginning, working in an agile manner. So you build this whole pipeline to begin with, but you build it simple. You only use simple models. You only use features that are easy to compute and are already available in serving time to begin with. So you have a fast first iteration. And after you set up this baseline that you can measure and you see the impact of your work, you can know whether you need to iterate on it or not, whether you actually need to add this fancy, very complex features or add thousands of layers in your neural network, do some hyperparameter tuning. It's not needed for every case. It's also very, very important to mention that in order to do this right, you have to treat a data scientist as an engineer, which means a data scientist owns code in production serving hundreds of millions of users. This code has to go through code review. This code has to be unit tested. The data scientist actually designs a full cycle of a production system. This system needs to have a proper architecture and see if the tooling that's we use and the architecture, software architecture that we have fits the company's architecture, which in Google is a process called design review. So you have to do that. Now, you have to articulate these processes, teach them to your data science community. And very important for Velocity is creating this template of codes and documents to be able to do it right, fast, and facilitate smooth work for your data scientists and not have them invent all of it from scratch. Because tools be tools, there's a lot of boilerplate here that is just copy paste, and you can abstract away and not even have the data scientists need to touch them or copy them. They're just automatically inherited. You only do your feature engineering and modeling. That's it. And in these extreme 10% or under 10% cases when you need to customize something, only then you customize this boilerplate code. Does this actually work? Well, yes, it works really well. I really recommend you to try full cycle data science. It really shortens the time from idea to production. It makes data scientists independent and have them contribute independently to production. It eliminates the need for re-implementing code in another language or in a scalable manner. And we have a bunch of success stories piling up for them. I've linked here, once you get a presentation, for a blog post that we have on one of these success stories. You're welcome to read that. And that's it for me. So I want to thank you for listening to this talk. I'm hoping that it was helpful and you will take some of it and adopt it for your use cases, only the parts that you feel like would be helpful for you. And I want to remind you that there is Summit Slack where I'm right now available and you can ask me anything. If it's regarding this presentation, anything else that I've talked about, anything else that you're interested in on machine learning and you think I can help with. So I was Daniel, and it was nice talking to you. Thank you.